Welcome back to the channel. Today we're diving into one of the most critical concepts in materials science and mechanical engineering: fracture toughness. Why do some materials snap suddenly, while others resist cracks and keep holding together? The answer lies in their fracture toughness. Let's break it down. Fracture toughness. It's one of the most critical mechanical properties in engineering, but unless you're deep in materials science, you might not realize just how much it shapes the world around us. Let's break it down. At its core, fracture toughness is a material's ability to resist the propagation of a crack. So, if a material already has a tiny flaw, maybe a microscopic crack or an inclusion, fracture toughness tells me how likely that crack is to suddenly grow and cause catastrophic failure. It's measured in megapascals times the square root of meters. Now, not all materials are created equal. Metals like steel typically have high fracture toughness. They can absorb a lot of energy before breaking, even with some cracks present. That's why steel is used in things like bridges, skyscrapers, aircraft. Ceramics have low fracture toughness. Glass has low fracture toughness. They're strong, sure, but if a crack starts, it spreads fast and the material shatters with little warning. Polymers? It depends. Some, like certain plastics, can be quite tough, while others are brittle. Even within metals, there's a huge range. Aluminum alloys have different fracture toughness values. Titanium alloys have different fracture toughness values. Processing, like heat treatment, can dramatically affect toughness. So why does this matter? In the real world, no material is perfect. Manufacturing always introduces tiny flaws. Daily use creates more. If I'm designing a jet engine blade or a pressure vessel, I need to know, if a crack forms, will it stay put, or will it zip through the part and cause a disaster? That's where fracture toughness comes in. It lets engineers predict failure well before it happens. For example, the aerospace industry uses fracture mechanics to set inspection intervals for airplanes, ensuring cracks are detected and fixed before they can grow too large. In civil engineering, fracture toughness determines how thick a bridge cable or a gas pipeline wall needs to be to avoid catastrophic rupture. Even in everyday life, choosing a smartphone screen, choosing a bike frame, fracture toughness helps balance strength, weight, and safety. To sum it up, fracture toughness is the unsung hero that keeps our engineered world safe. It's not just about how strong a material is, but how well it handles flaws. Because in the real world, flaws are inevitable. Understanding fracture toughness is what allows engineers to push materials to their limits without crossing the line into failure. That's why when I look at any complex structure, I know there's a whole world of fracture mechanics at work, quietly preventing disaster. Thanks for watching. Don't forget to hit the like button, subscribe for more materials, science and engineering content, and drop your questions in the comments below.